Okay, this is week 4 in DSIM 525. We are going to cover random variables and probability distributions. These are important to our future analyses, in particular, verifying assumptions of other models we're going to learn. The most important distribution is the normal distribution, but we're going to talk about a few others today. Let's start with talking about random variables. A random variable is a variable that assumes numerical values associated with the random outcomes of an experiment, where one and only one numerical value is assigned to each sample point. The first kind of random variable is called a discrete random variable, which are random variables that can assume a countable number, finite or infinite, of values. Here are a few examples of discrete random variables. It's anything that is countable. So if we were to count cars at a toll plaza between 11 and 1, then we would have the number of cars arriving, and it would be some countable number. On the other hand, the other kind of random variables are called continuous random variables, which are random variables that can assume values corresponding to any of the points contained in one or more intervals. So there are values that can be infinite but are uncountable. Here are a few examples. If we had 100 people show up, then the random variable of their weight would be continuous because weight can be measured in any interval, as we could break it down into pounds and then down into ounces and then into grams, etc. So the fact that you could use a decimal and you can get continuously smaller in how you measure. Our first concern is with discrete probability distributions, which can be graphed, they can be in table form, or as a function or formula, and gives the possible values of that random variable. The requirements of a discrete probability distribution are that we have the probability of all possible values of x, and thus that those probabilities sum 1. If we look at an example of a probability distribution, here we have 2 coins and want to know the probability of tails. The possibilities are that we can get 0 tails, 1 tail, or 2 tails on the 2 coins. We have a 1 in 4 chance of getting 0 tails and the same for getting 2 tails. For getting 1 tail, we have 2 in 4 chances. We can visualize those probabilities in many ways. A probability table is the easiest to read and use. We have the number of tails as of interest to us. If we get 0 tails, then that is one possibility, and there's a 25% or 1 in 4 chance of that occurring. If we get 1 tails on either of the coins, then there is 2 possibilities that we can count, giving us a 0.5 or 50% probability. And if we get 2 tails, then the probability is 0.25 because there is only one possible outcome that will give us 2 tails. We can also look at this in a bar graph where 0 is 0.25 and 2 is 0.25, but between these two, something that might be useful is if we wanted to add the probabilities of 2 different events. So if we wanted to add the probability of getting 0 tails to the probability of getting 2 tails, then it would be 0.25 plus 0.25. So probability of getting no tails or both tails is 0.5 or 50%. This is the formula to calculate out the probability of X. We'll come back to that in a second. We can create summary statistics for these discrete random variables. In this case, it is a discrete binomial random variable for the heads and tails example. The mean is found by multiplying the sample size or number of trials n times the probability you are interested in. The variance is found by taking the weighted average of each of the values of X times the probability of that particular outcome of X. I have also created a spreadsheet to assist with this on a binomial random variable. So here you have a probability, let's say, of 0.5, and you run 10 outcomes. It will calculate out your mean, your variance, and your standard deviation. A binomial distribution is built off of a variable that can have only two outcomes, such as heads or tails, or the number of correct answers on a test. You are either right or wrong, and thus there are two potential outcomes. When we calculate probabilities for a binomial random variable, we will require a sample size n. There can be only two possible outcomes for each sample or trial, and that the probability remains constant on each sample. So this is the formula I said we would come back to. Basically, we want to find the probability of X. We have P, our probability of successes. So in this heads or tails coin example, tails on a single trial. We have we have Q, which is 1 minus P. So that's the complement to the probability of P here. We have N, which is our number of trials or our sample size. X is the number of successes, so this is the number of actual tails we got. And the number of failures would be the other side of that, which would be N minus X. So I've created a small calculator to do that also, to find the probability of a binomial random variable. Let's say we flipped a coin 10 times. We got tails 5 times, and we had probability of getting tails is 0.5, so it will calculate our probability of X here. The Poisson distribution is a discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time or space. If these events occur with a known constant rate and independently of the time since the last event. Here are a couple of examples, but this distribution is most widely used in simulation and queuing problems, like the number of arrivals to a cashier per hour would be Poisson distribution. Or a bank teller is a really common problem that uses the Poisson distribution. This is the formula to calculate out Poisson probability distribution. I've created another calculator because there is a formula built into Excel that will allow you to calculate that out. So if we are looking at the probability of X, and we have a mean of 5.4, we can calculate all of our probabilities. Probability of X less than or equal to 5, 0.546. Probability of X being greater than or equal to 5, 0.627. And this is all based on the Poisson distribution. The normal distribution is the most important. Most of the statistical tests we run assume a normal distribution. Hence, number 3 is the basis for our classical statistical inference. The normal distribution is your typical bell-shaped curve, and the mean, median, mode are all equal. It also has a skewness of 0 and a kurtosis of 3. We use the normal distribution to find the probability under the curve. This gets into calculus, so we won't go that far into proving the formula, but we will want to find the area under a curve in the tails when we get to hypothesis testing. So in particular, either the lower right or both tails. When we do hypothesis testing, we're going to have to find a z-score or t-statistic in order to calculate our p-value. And this formula is what we utilize to accomplish that. I've created a calculator here that will help you calculate out your z-score. You just need the mean, the standard deviation, and your x value. The last distribution I want to discuss is called the uniform distribution, and it is a continuous distribution that has an equal likelihood of occurrence for each value. So in this distribution, we find the probability between 2 points, which is going to be the uniform frequency function. We can also calculate our summary statistics on this distribution, in particular the mean and standard deviation. And on the last tab, I have created a calculator to calculate that out for you. So you put in your D and C values, it will give you the distribution function, it will give you the mean, standard deviation, and the probability between 2 points. I suggest if you use these calculators on your homework, you examine the Excel functions and try to learn how you can create spreadsheets like this to help you solve problems in the future. I think that is all for week 4. Most of this will become important when we start to get to analysis of variance and regression. Right now, we're starting to cover a lot of the fundamentals of statistics that we need to know before we start actually using them to make decisions.